Hello. In this video we will outline the basic procedure for evaluating limits. We will actually assume that you already heard about limits. Perhaps you attended some lectures, perhaps you read some theorems in some book. So what we will do here is to try to offer a practical point of view. We'll try to show an algorithm. Now this algorithm uses several ingredients, 3 of them perhaps, depends how you count it. And one basic ingredient is elementary functions. We will assume that you are familiar with them. In particular, that you know how they behave at the endpoints of the domains. And this can be captured in some symbolic way. For instance, the exponential e to x. When we look at it at infinity, the limit is infinity. We can write it like that. Now, this is just a sample. Of course, there are more elementary functions. But these are the most popular expressions that we need. And when we look at them, it looks as if we simply substituted infinity into exponential or logarithm. And this is a very practical way of looking at it. And in fact, this can be considered a part of so-called limit algebra, which is the second important ingredient. Limit algebra is basically the usual algebra, like 2 plus 3 is 5. Yeah. And we also add some infinities into the mix, and we get new expressions. Most of them are fairly obvious. When you just think about them, you don't really have to memorize it. For instance, when you take a real number and you add infinity, you get infinity. Makes sense. Common sense. So there are many rules like that, and you can look them up. So this is just a sample again. The third rule, it actually reminds us of one important notion, which is a one-sided limit. So if you are not really familiar with one-sided limits, perhaps you can check out my bonus video about them. Which brings us to the third ingredient. Limit algebra allows us to do calculations, evaluations. But sometimes we are in a situation when this fails, and it's important to be able to recognize such cases. And these are the most famous cases. These are called indeterminate expressions. Now, I group them according to, let's say, practical point of view again. These three, 0 over 0, infinity over infinity, 0 times infinity, these are probably the most usual indeterminate expressions that we meet, and we have a procedure for them. Infinity minus infinity, that's also fairly common, and it's one which is obvious. When you are subtracting two huge expressions, you cannot really tell what the outcome will be, because it depends on which of these infinities is larger, in quotation marks. The last three, these are a little bit tricky, at least some of them. Because, for instance, one might think that 1 to infinity should be 1. Well, sometimes yes, but sometimes not. We don't know. That's why they are called indeterminate expressions. And these three, because they are not all that intuitive, perhaps it's a good idea to memorize them. I actually did. So, these are the basic three ingredients that we are using in our limit approach. So how do we calculate limits using these ingredients? Well, we will look at the most common case. When you get a function which is given by a formula, some algebraic expression involving elementary functions, algebraic operations, perhaps some compositions as well, and you are supposed to find a limit at a certain point A. And the first step is very simple, and sometimes it's enough. You simply take the limit point, this A, and you try to substitute into your function, and then you try to evaluate. And if you get lucky, you get an answer. So that's one possible outcome. You try it, and it works. That's a very nice case, and you get your limit. So let's have a look at an example. Okay, so here's our example. That's a fairly typical example, because I can see an expression here, which involves some elementary functions like logarithm, exponential. I can see algebraic operations, division, addition, and I can see composition. 1 minus x, which is a polynomial, is substituted inside the logarithm. And I'm supposed to evaluate limit as x goes to 1 from the left. Now, the basic step says, take number 1, substitute it into this formula, and see what happens. Okay, I'm going to analyze it here on the left. And after I substitute number 1, I get 1 over logarithm 1 minus 1, and this one is taken from the left, plus e2 1 taken from the left, plus 1 over 1 taken from the left minus 1. Okay, let's see. 1 over logarithm at 0. And now it's time to talk about one-sided limits. When I'm approaching 1 from the left, I'm actually taking numbers which are somewhat smaller than 1. And when I subtract them from 1, I get something positive. So I'm approaching 0 from positive numbers from the right. So it's a positive 0. OK. E to 1 from the left. Here, the one-sided information is not really relevant. It's simply e to 1. And the answer is e as a number. It's not an exponential anymore, just a number, 2.7182818, and so on. You know it. OK, let's move on. 1 over. 1 minus 1 is usually 0. And this is 1 from the left. So this is a number which is somewhat smaller than 1. And I'm subtracting 1, so the outcome will be negative. Small negative numbers. This is a negative 0, or 0 minus. OK, let's move on. Logarithm at 0 from the right. Well, it's in my dictionary. This one I remember, negative infinity. Plus. E is a number. Plus. 1 over 0, negative, is negative infinity. OK, one more step. 1 over infinity is 0. Minus in front of it, I don't have to worry about it. But I just put it there so that we can see that it doesn't disappear. I'm adding exponential. I'm subtracting infinity. And I'm ready. 0 plus e is just e. Minus infinity is a negative infinity. And that's the outcome. So that's the basic rule in action. You take the number, you substitute, you evaluate using limit algebra, if necessary. And if you get a definite answer, something that makes sense, that's the outcome of the limit. Wonderful. That was easy. OK, let's talk about the other possibility. So we take the limit point A, we substitute, and it doesn't work. In that case, we have to do something. And what we do really depends on the kind of failure that we have. So there are, again, two cases. And the first possibility is that already the first stage in the substitution failed. So I would say failed substitution. How does it happen? Well, let's try an example. Imagine that somebody asks for a limit of this expression when x goes to 2. So we start substituting. By the way, why did I write it separately? Well, because some people accept this as a proper calculation, so they can use it in the calculation. But for some people, this is not really proper mathematics. You know, there is no universally accepted way to express how to write down such a calculation, such a reasoning. So if you are not sure, it's better to do it on the side somewhere and just copy the answer. But perhaps if you are taking a course and the prof is fine with it, you can use this as an official calculation. It really depends. So let's try the same unofficial or official calculation for x going to number 2. Well, we take number 2, we substitute, and we get 1 over logarithm of negative 1. And that's a nonsense, of course. Now, you may argue that logarithm at 0 is also nonsense. Let's think about it. Logarithm 1 minus x. What's the domain? Well, when you think about it for a few seconds, you will see that the domain is the interval from negative infinity to 1. Here we go. So we are not allowed to substitute number 1 into this expression, which we did over here. But number 1 is exactly at the end point. And what's more, we are approaching it from the left. We are approaching it from the region where this function exists. So it's perfectly OK to do it. And we have limit algebra, which tells us the outcome of such a substitution. So this was a proper step. On the other hand, number 2 does not lie at the end point of the domain of our function. It lies farther apart. And we are not allowed to make such a limit or to take it or to ask for it. This is not a proper limit. The definition of the limit doesn't allow it. That's the proper mathematical way to say it. So this calculation simply cannot be done. And if we get it as a problem, we are supposed to answer it Well, how would I answer it? I would say the question doesn't make sense. Yeah, that's an answer. The question doesn't make sense. Now, quite frankly, you don't expect to see this very often. Most likely, when you see a problem like that, somebody made a mistake. Most likely, they were trying to make up a nice problem for you and they slipped somewhere. Right? But if it happens, if you see a problem like that, now you know how to handle it. Okay, this leaves us with the second part, with the second branch. So we try to substitute A. It doesn't work. We didn't reach some nice answer, which is what we want. But the first step actually worked well. We took the number, we substituted, and it looked okay. But then we somehow stopped on the way, and we couldn't go on. The limit algebra failed us. So I would say failed evaluation. And that's the most typical case that you can see on tests at the exam, because such problems are interesting. You know, this is sort of boring. You just put it in and you get the answer. Very easy, too easy. So what you most likely meet at exams is exactly this box, failed evaluation. So let's have a look at it in detail. Okay, so here's the situation. You took your limit point A, substituted it into your function f, and the first stage went okay. But then, when you tried to evaluate further, you hit some point where you couldn't go on. Something went wrong. Now, what should you do? Well, the information what went wrong is actually very useful. It can guide you. And if you're lucky, you encounter one of these indeterminate expressions. Because for each of them, there is a very good guide, which most of the time works. Okay? So let's have a look at it. That's one branch in our decision tree. That's a decision tree. Indeterminate expressions. Well, the best thing you can get is indeterminate ratio, because for that we have a nice trick called L'Hopital's rule, which works most of the time. Not always it's the best option, but it's fairly reliable. The next possibility we will look at is the indeterminate product. Well, here the recommendation is to just take it as an algebraic expression and rewrite it so that it looks like a fraction. Now there are two general approaches. One of them is that you keep, let's say, the zero part, and you take the infinity and move it into denominator. What you get is a fraction, 0 on the top, and 0 in the denominator, and you are here at this case. And you can use L'Hopital's rule. Very nice. And of course, you can do it the other way around. You keep the infinity on the top, and you take 0 and move it down. And this is of the type infinity divided by infinity. And again, you can use L'Hopital's rule. So that's a very nice case as well. Okay, let's move on. Indeterminate power. For this, there is the following recommendation. Take your expression and take logarithm of it, and then the exponential. So your power stays the same if you do these two operations, but it starts looking differently. It will look like exponential with g times logarithm of f. And if you try to work it out backwards, you will see that these two expressions are exactly the same. But the point is that the problem which was here in the power now moved into a product. And we know how to handle products. And if you are lucky, while working this, you actually obtain a ratio here, and then you just apply L'Hopital with a little bit of work. Okay, so that's also a very nice case. The last indeterminate expression is the indeterminate difference. Now, there is a general procedure which will change it into a ratio, but it's quite complicated. So very often you can actually do it in an easier way. You just look at these formulas that you can see here, and you ask, can I write them in such a way that it's just one compact expression? For instance, by using a common denominator. Sometimes this works. Or perhaps you can factor out something out of both expressions. So this is actually quite individual. It depends on the question, how you handle it. So this is slightly different compared to the previous cases, because there is no clear-cut procedure for that. Rather, there is a general advice. Now, these are the indeterminate expressions, but your limit could have failed, or your limit evaluation could have failed for different reasons, which are not of this form. For instance, there is a popular situation when you end up with infinity inside the sine function or the cosine function. Now, sine at infinity does not really make any sense, and we cannot assign answer to it. So if we encounter something like that, limit algebra does not help us, which is quite sad, but that's life. So there are some tricks for situations like that. For instance, the squeeze theorem or some comparison theorems. So this is like a special box which has its own approaches. Or there is another box which is called square root minus square root. Some expressions are like that, and there is a special trick for that. Or perhaps you encountered a ratio of two polynomials which is taken at infinity. And again, this is a special category. So here we have indeterminate expressions, and here we have some tricks which are based on the shape of the expression. And there are many more. So here we had rather clear-cut procedure, and here we have many ideas. And essentially, it's hard to learn it somehow by heart. So what you need is experience. And if your limit falls into this part of the tree, then the more limits you actually evaluated before that, the better your chances of exceeding. Okay, so that's the general decision tree. That's the general outline of the procedure. And most limits that we will encounter can be handled using this approach. So now we will look at an example. Okay, x squared divided by x squared plus 1. This all raised to the power x squared. And we are looking for limit as x goes to infinity. So the first step is to just take infinity and substitute. Let's see. Infinity squared is infinity, divided by infinity plus 1. This all to infinity. Infinity plus 1 is just infinity. And that's the end of the road. Here we can see indeterminate ratio, which wouldn't be so bad. We could apply L'Hopital's rule, but unfortunately it's taken to power infinity. And for this expression, we don't really have any bracket here. So what do? Well, we can notice that the base of the power is a ratio of polynomials. And there is an approach which works quite well at infinity. And what it says is this. From each polynomial, identify the dominant power, the highest power, and all the other become irrelevant as you go to infinity. So in the denominator, the plus 1 part can be ignored. And if you ignore it, it's just x squared over x squared, which is 1. So the base at infinity gives me 1. And now we have 1 to infinity, which is an indeterminate power. So finally, we know what to do because we are here at this situation. We are supposed to rewrite our expression using this trick. So let's go. We take limit as x goes to infinity, exponential, and then we put logarithm of this whole expression. And when we take logarithm, we can pull the power out. And then there is logarithm of the base. X squared over x squared plus 1. Now let's have a look at it. When we substitute infinity into x squared, we get infinity times. And we substitute into this ratio, it becomes 1, and logarithm of 1 is 0. Infinity times 0, that's an indeterminate product. And we have a procedure for it, which is wonderful. Unfortunately, this procedure leads to L'Hopital's rule, and L'Hopital's rule cannot be applied to exponential. This exponential is getting in the way. But fortunately, there is a theorem which says if you have a composition and the outer function is continuous, you can pull it out, which is exactly what I'm going to do. I take the exponential, pull it out of the limit, and the limit itself is now applied only to this exponent. And now we are ready to evaluate this limit, which is much easier than this one. Okay? Actually, I don't really feel like continuing in this calculation. Why not? Well, I would have to carry the exponential with me all the time. And I don't actually need it for any calculation. It's just there. So I'm going to do a little step aside over here. And I will focus just on this limit. And I will evaluate it. And after I get the outcome, I will come back and substitute into the exponential. So this is a little reminder to myself that I should come back here with my answer, which I get over here. Okay? So let's have a look at it. I am trying to evaluate limit as x goes to infinity of x squared times logarithm x squared over x squared plus 1. And we already saw here that it's actually an indeterminate product. So what's the advice? Well, the advice is take the product and change it into a fraction. Here we go. I copy the limit part. This I have to carry with me all the time until I get to the answer. Okay, I have two terms. One of them should be left on the top. Which one? Well, I think that this one is already complicated enough. I don't want to make it even more complicated by putting it in the denominator like that. So I will keep the logarithm on top. And I will divide it by, and I take this and move it down, and it becomes x to negative 2. Okay? Now we have a fraction, and it should be indeterminate fraction. So let's check. X squared over x squared plus 1 at infinity is 1. We already saw it. And logarithm of 1 is 0. Infinity to negative 2 is also 0. Those negative powers, they are a little bit tricky. So personally, I prefer to see this as 1 over x squared. This is what I see there. And then I substitute infinity into it, and its infinity square is just infinity. And 1 over infinity gives me 0. Okay? Anyway, 0 divided by 0 calls for the L'Hopital's rule. I have to copy the limit picture. And now the rule says, differentiate the numerator and differentiate the denominator separately. No ratio rule in here. So, I'll start down. Derivative of x to negative 2 is negative 2 times x to negative 3. Well, that was easy. Half is done. Good. Now the derivative of the numerator. This is a composed function, so the chain rule says differentiate the outer function, which is logarithm. Derivative of logarithm is 1 over whatever is inside. So it's x squared over x squared plus 1. So that's the derivative of the logarithm. Now we move inside and differentiate the ratio. So that's the ratio rule actually now. So how does it go? Well, it's probably longer. Okay, I should square the denominator and now differentiate the top, 2x, times the denominator, x squared plus 1, minus the top, x squared, times derivative of the denominator, which is 2x. Okay. So we have a new limit, and we basically start right from the beginning. We should take the infinity here, substitute and see what happens. But when you look at it, you say, oh, wait a second. I would prefer to make it nicer, which of course we can. So I'm going to make one large fraction. That's enough, hopefully. What do I see here? Negative 2 in the denominator. X to negative 3 should be in the numerator as x cubed. That's the right place for it. This little ratio gets flipped around. So it means that x squared plus 1 ends up on the top and x squared down here. And then there is another ratio, so x squared plus 1 squared goes down. And on the top, there will be 2x cubed minus 2x cubed. This cancelled, nice. 2x, that's it. I can still cancel this part with this part, 2 with 2. And let's see. There will be x squared plus 1 left in the denominator. And in the numerator, there is x cubed times x is x to the power 4, but there is x squared here, it cancels, and I get just x squared. That's nice, I like it. By the way, that's exactly the same expression that we were investigating here, just intuitively. So now we have a chance to actually calculate that it really yields 1 or negative 1. I forgot about the minus sign. We should be careful. Okay, let's go. I look at it, I substitute infinity, and I see that it's infinity divided by infinity, and the minus sign doesn't really make any difference now at this point. So that's a typical case for L'Hopital's rule. And the L'Hopital's rule says, differentiate in the numerator, differentiate in the denominator. Now we can cancel. And now we are ready to evaluate. This limit is negative 1. And after such a long work, it's easy to just feel, yeah, I did it, and forget that actually the real calculation goes on here. This was actually a sidestep. So this outcome should be copied over here. And this is the correct answer, e to negative 1. Well, it was a little bit longer, but there was nothing tricky here. These are straightforward calculations. And that's the most typical example of a limit that you will encounter. You just look at it, you analyze the type, and you apply the appropriate procedure, just like we outlined it over here. Okay? So as I said, this is the most typical case that you will encounter, and the recommended procedure works quite well. But sometimes it's worthwhile to think of some alternative ways. Perhaps they are easier. So let's make some room. Okay, so what's the alternatives? Well, I see one. Right at this place, it's possible to take L'Hopital's rule, which we did, but also one could try a different trick. So let me do it over here. I'm interested in limit x going to infinity of negative x squared over x squared plus 1. Now, what we see here is a polynomial divided by polynomial taken at infinity, and for this there is a nice procedure. We talked about it intuitively. We are ignoring powers which are not dominant, and if we want to do it properly, then there is a good advice which says, in each polynomial, factor out the dominant term. Well, we already have it on the top. It's factored out. And in the denominator, we can factor out x squared, and we get 1 plus 1 over x squared. And now we can cancel. So the dominant term disappears, negative 1 on the top, and 1 plus 1 over x squared in the denominator. And now we are ready to evaluate. When you see a process like that, you can notice that we could actually take this expression and just cancel x squared. This is sometimes possible. And if you're experienced, you can guess beforehand that it's a good idea. But unfortunately, it doesn't work always. But this factoring out business will always help you. That's the difference. Anyway, now we substitute infinity. 1 over infinity is 0. So we can see 0 over here. Negative 1, 1. The answer is negative 1. Exactly as we had it before. So that checks. Okay, so that was one alternative. Let's see. Well, when you look at it, there is not really much you can do because these are fairly straightforward calculations. So if you want to try something else, you have to go to the very beginning. And I will show you an approach which is, well, perhaps not so useful. It depends on what you know. And it's a little bit interesting. We will see. So take it as a bonus. Alternative. I will start right here with the limit as it is given. So we take x squared over x squared plus 1, that all to x squared. And my first step, and this is a fairly useful trick, is to add and subtract 1 in the numerator. Why am I doing it? Because if I do it, I can divide with remainder. So if I put plus 1 here and I divide, I simply get 1. And then I have to do negative 1, and that will be the remainder part. And that all to x squared. Now, why is it useful? Well, actually, this expression is sometimes easier to handle. For instance, if we send x to infinity, then this obviously goes to 0, and we can see that the base really tends to 1, which is something that here we investigated using this intuitive approach. Here we can see it right away. Also, we were trying to take derivative of this ratio. But if you're trying to take derivative, it may be easier if you see it in this way, at least for me and for many people. This is a little bit easier to differentiate. So that's a nice expression. But that's not the main reason I was doing it. Okay, here is a trick. I'm going to take the expression x squared plus 1 and call it y. So this, in fact, is a substitution. Now, you probably know substitution from integrals, but it can be also used in limits. Let's see what we get. Limit 1 minus 1 over y. That's very nice. And the basic rule of substitution is that x must disappear. The second basic rule of substitution is that we cannot just make it disappear. We have to follow the basic formula that we chose right at the beginning for the substitution. So, x squared, how do we make it disappear? Well, from this formula, I can easily figure out that x squared is y minus 1. And finally, there is one x over here in the limit specification. It says that x goes to infinity. Now, using the formula which we have here, when x goes to infinity, y should also go to infinity. So this tells us what to write here. And we have a new limit, and there is no x in the picture, just y's everywhere. That's how it should be. Is it nicer? Well, it depends. Whether you know the following trick. Let's see. One more step. I'm going to do two things. First of all, I'm going to get rid of this negative 1 in the power. So I will split it into two groups. One of them is 1 minus 1 over y, this all to negative 1. And what is left is power y. And I'm going to change the base slightly. I will write it as 1 plus negative 1 over y. Now, why was I doing it? Well, as I said, it depends on your background. Some students actually have to memorize by heart this limit. When I was a student, I had to memorize it. So if I memorize it, I can just look at it and say, okay, this is e to negative 1. And this is 1 to negative 1. So this is all e to negative 1, which is the correct answer. Yep, checks. So I guess there are many students who actually didn't memorize such a limit, and for those students, this is not really a good way to solve it. But still, this substitution trick can be sometimes useful. So this is it for this example. And that's it for the video. There will be a few more examples in another video. See you.